Our last module regarding relations will focus on the property of closure of relations. The idea of closure of relations is based on what we saw earlier about reflexive, symmetric, transitive properties. We looked at whether a relation is reflexive, symmetric, or transitive in that context. Here, what we're going to look at is it possible to make a relation, change the relation in a way that will have that specific property? So, if I have a relation that's not symmetric, but I would like to make it symmetric, could I do that? Most of the time, when this is used in practice, it is used where we add new pairs to the relation to make it have that specific property. Occasionally, you might see it also where you're removing certain things to make the relation have that property, but most of the time you will be using it where you add new things to have that property. So, first of all, to understand the concept of closure, I want you to think about a couple of examples. The first example is the set of natural numbers. So the set of natural numbers are closed under addition because if I take two natural numbers and I add them, what I get is a rational number. What I get is a natural number. However, it is not closed under subtraction because you can do 1 minus 2, which is not a natural number. So let's consider the problem. I would like to make natural numbers closed under subtraction somehow. And these are the rules. I'm not going to be able to remove anything, but I can add some things. So I can take a superset of natural numbers and I would like it to be closed under subtraction. Now, there are many such sets that you could have. You could have the set of integers, you could have the set of rationals, you could have the set of reals, you could have the set of complex numbers. All of them are going to be superset of natural numbers, but they are closed under subtraction. What we want is the smallest such set, and in this case it will be the set C, which is the set of integers. So that's basically what we want in the definition of closure of natural numbers under subtraction. We want a superset of n, but the smallest such possible set. And in this case, it would be the set of integers. Let's look at the set of integers w except for the number 0. It is closed under multiplication. If I take two numbers in this set, their product is in this set. It is not closed under division because half is not an integer. If I wanted to have closure under division, then I want all integers plus I want some more things like half, 1/3, 2/3, and you can see that the smallest such set is going to be the set of rationals. So what we want to do when we get a closure is we start with the set we have and we add more things in order for that set to have that specific property, and we want to add as minimally as possible. Okay, so we want to look at closure of properties, which is if the property is not true for my current set or my current relation, how could I minimally augment the relation, add to the relation so that the property would hold? Now let's consider this relation. Suppose we want to make it reflexive because it isn't. So what is the smallest addition I can make to this relation so that it will be reflexive? Clearly, it's going to be adding the pairs 2, 2 and 3, 3. So what is the reflexive closure of a relation R? Essentially, if If the relation is reflexive, you're already done. If it's not reflexive, add minimum number of pairs to make it reflexive. Essentially, it would be adding self loops that are not present in the relation already. So we can define it as, we can define the diagonal relation AA, where A is in A, and the reflexive closure is going to be R union, this new diagonal relation. R is going to be a subset of this. The R union delta is going to be reflexive. And if I had found any superset of R that was reflexive, then it would be at least as big as the relation that we got. In other words, this is the smallest such relation. So if I think about this in terms of this graph, then adding reflexive closure is basically adding the self loop at every point where there isn't one. So at 1 you already have a self loop, so we added 2, we added 3, and that is going to be the reflexive closure of that relation. Let's consider an example. Here we have the relation AB where A is less than B. If I wanted to get the reflexive relation, then basically I have to add the diagonal relation, and I will let you check that essentially if I want to make this reflexive, then this less than would be changed to less than or equal to. Symmetric closure is a little bit more complicated, but the idea is the same. We want to add as little pairs as possible to make it symmetric. So here the relation is not symmetric because I have 1, 2, but I don't have 2, 1. So to make it symmetric, I'll have to add that. I have 3, 1, but I don't have 1, 3, so I'll have to add that. And I'll have to keep doing that for every pair. And when I have added all these, the relation would be symmetric. So if a relation R is not symmetric, then if we want to augment it with minimum number of pairs, that's what is going to give us the symmetric closure of R. Now, the way we can compute symmetric closure is fairly straightforward. We can look at the inverse of the relation, which is if the pair AB is in relation R, BA is in the inverse of R. And I would ask you to verify that the symmetric closure is going to be R union R inverse. And I want you to verify that this is in fact a superset of R. It is symmetric, and it is the smallest set for which it is smallest superset of R for which the symmetric property is satisfied. In terms of graphs, this basically corresponds to adding the reverse of the links that are present. So here we have the link from 1 to 2 that is here. So we are going to add this link 2 to 1. So if I look at an example, I have here a relation AB where A is less than B. If I wanted to get symmetric closure, then I want AB where A is less than B, or where B is or where B is less than A, and that's going to give me essentially the relation AB where A is not equal to B. Transitive closure, the idea is same. Keep adding pairs, minimum number of pairs to make the relation transitive. So what are some of the missing terms? So here I have 1 3 3 2 that expects that I have 1 2. I don't have it, so I should add it. I have 2 1 2 3, so I expect to have 2 3. I don't have it, so I add it. Now if we add those, we will get this relation. Now is this transitive? It's not, because at this point it's still missing some terms. It's because when I added this pair to 1, it could combine itself with another pair to get 1 1 or 2 2. So I have to add that, and I have to keep doing that. And so that makes transitive closure a little hard to construct, but that's basically what you're doing. You find a pair AB and PC such that such that AB and PC are in the relation but AC is not, then you add it. That might require you to redo the work to add more pairs and so on. But at some point you will stop. At that point you would have obtained the transitive closure. We can think about transitive closure in the graph like this. So here there is a path from 2 to 3, sorry, 3 to 2, then 2 to 1. Then we are going to add this 3 to 1. Essentially, this means if there was a path to go from one vertex to another, then I'm going to add an edge. If there was a multi-step path I could take from one vertex to another, then I'm going to add a direct edge between them. And that's how I'm going to get transitive closure of the given relation. So some of the examples of things that would be added would be like this and like this. So the definition of transitive closure is again similar to what we saw before. Minimally augment the relation R so that it has the transitive property. Next, we will see a couple applications of closure properties. The book has several others, and in fact, closure properties are useful for lots of different things as well. So here is a problem. You are given a graph and you would like to know whether two vertices in this graph are connected to each other. Now, what is a path? Path is, if I wanted a path from A to B, that means I have to start from A, I have to connect to some vertex x1, then x2, then x3, and so on. Eventually, I should go to B. This path is what we'll call A, x1, x2, all the way up to B. It has length n, where n is the number of edges that you traversed. If A and B are same, then the path is called a cycle or a circuit. Now, here is an observation that we can make. Let R be a relation on set A. The relation is describing the edges in the graph in the previous examples. There exists a path in relation R of length n if and only if the pair AB is in R to the power n. Now, I'm not going to do a proof of this, but I want you to be able to see why this is true. Specifically, if there is a path from A to B of length n, then uh, then the pair AB would be in R to the power n and vice versa. Once again, we have reached the check before you go ahead slide. So here we have studied closure of a relation. Closure of a relation has few important things. It adds new pairs to the relation. It does not remove anything. The goal is that the pairs that we add must be minimal, so we don't add all possible pairs that could be added. Yet another goal is we achieve the desired properties. So we have reflexive closure, symmetric closure, or transitive closure. So that means we want to get that property. Now, we did not study irreflexive or antisymmetric closures. Try to see if you can understand why that is the case. If you if you think about what is on this slide, uh, and you're able to answer it, it will go a long way to understanding what closure of relations is. If you're still having trouble, please check with somebody from the instructional team. We have reached the end of the module, so please go ahead and do the review quiz.